72 hours. That's all that stands between us and what could be the most profound revelation in human history. Right now, an object from beyond our star's three-eye atlas is rapidly approaching the Sun. Some call it a maneuver, others call it a message. According to Dr. Michio Kaku, everything hinges on one impossible question: will it gain energy it has no right to have? If it does, then this isn't a comet, it isn't an asteroid, it's something conscious, something aware. What happens in the next 72 hours could determine whether humanity has truly been alone, or if we've been quietly watched all along. So don't blink. By the end of this video, you'll grasp the exact measurement that could expose intelligence hiding in plain sight. If this mystery fascinates you the way it does me, don't stay in the shadows. Hit like and subscribe so you won't miss a single update as this unfolds in real time. Drop a comment telling us where you're tuning in from, what time it is, and your thoughts on this new development. And if you want to help this community grow, share this video on X, Facebook, Reddit, or even in your group chats. You're the reason we can keep chasing stories like this. Thank you for having our back. Part 1. The Stakes. October 29th, 2025. In just 72 hours we could learn whether Three-Eye Atlas is alien-guided. Right now, as you watch this, an object from beyond our solar system is speeding toward the Sun at nearly 58 kilometers, faster than anything we've ever launched. It emerged from the infinite dark between the stars, and in 3 days it will perform what theoretical physicist Michio Kaku calls an intelligence test. If it passes, everything changes. If it fails, we're still left wondering if anyone else is out there watching the same stars we are. This moment has captured global attention because the stakes are immense. We're not simply talking about discovering a new comet or cataloging another space rock. We're talking about the possibility that an object from interstellar space might reveal itself to be under intelligent control. Kaku suggests that when Three-Eye Atlas swings around the Sun at its closest approach, scientists will measure something specific, whether it gains more energy than physics allows. An anomalous boost, a violation of conservation principles that would scream only one thing: propulsion intent engineering and the universe looking back at us. But before we get lost in excitement, we need to ground this conversation in reality. Kaku's claim is speculative, controversial, and not yet confirmed by peer review. This is not an established scientific consensus. It's a what-if scenario painted by one of science communication's most charismatic figures, someone who has built a career on making us imagine the impossible. That doesn't make it wrong, but it does mean we need to proceed with caution, holding both wonder and skepticism in equal measure. The line between revolutionary discovery and sensationalized misinterpretation is razor thin, and we're about to walk it together. Here's what we're going to do. This journey has 3 acts, 3 movements that will take us from the immediate science to the deeper implications. First, we'll unpack the core claim itself, what Three-Eye Atlas is, what Kaku suggests will happen at perihelion, and what would actually constitute proof of something extraordinary. Second, we'll dive into the hidden angles, the natural explanations we need to rule out, and the broader scientific context that makes this moment so full of potential and peril. Third, we'll connect this story to other cutting-edge developments in astronomy, physics, and artificial intelligence that are reshaping how we search for intelligence beyond Earth. Throughout, we'll remain speculative investigators asking tough questions, demanding evidence, but never completely extinguishing the flame of possibility. The central question is deceptively simple. If Three-Eye Atlas accelerates too much during its solar flyby, could it be evidence of extraterrestrial intelligence rather than just another comet? But hidden inside that question are layers of complexity. What does too much mean in precise terms? How do we distinguish between natural outgassing forces and deliberate propulsion? What error bars must we clear? What alternative explanations must we exhaustively eliminate before even whispering the word alien? The challenge is further complicated by timing. The data processing window around perihelion is incredibly narrow. Observations must happen in real time or near real time, with telescopes fighting against the glare of the sun, trying to capture precise positional measurements of an object moving at interstellar speeds. The margin for error is microscopic. The consequences of getting it wrong in either direction are enormous. Miss a genuine signal, and we let the most important discovery in human history slip past us. see a signal where none exists, and we trigger a global crisis of credibility in science itself. Kaku frames this as humanity's intelligence test as much as the objects. Are we sophisticated enough to detect deliberate navigation when it's right in front of us? Do we have the instruments, the models, the intellectual courage to recognize something that doesn't fit our comfortable categories? Or will we rationalize away the anomaly, forcing it into natural explanations through sheer institutional momentum? Because accepting the alternative is too disruptive to our worldview, the scale of what's at stake cannot be overstated. If 3I Atlas is confirmed to be under intelligent control, we're not just rewriting astronomy textbooks. We're rewriting SETI protocols, philosophy, and our understanding of our place in the cosmos. We go from being potentially alone voices shouting into an empty void to being observed, visited, perhaps even studied. The Fermi paradox collapses. The great silence ends. Everything we thought we knew about the rarity of intelligence, the difficulty of interstellar travel, and the loneliness of technological civilizations, all of it gets overturned in a single measurement. But here's the twist that should keep you watching. Even if 3I Atlas turns out to be nothing more than a chunk of frozen volatiles from another star system, even if it behaves exactly as gravitational physics predicts, we still learn something profound. We learn what interstellar matter looks like when it arrives at our doorstep. We learn about the composition of planetary systems dozens of light years away. We learn how to build better detection systems for the next visitor, and the one after that. The null result is valuable too, though admittedly less emotionally satisfying than first contact. So in 72 hours, regardless of the outcome we win, either we discover we're not alone or we sharpen our tools and wait for the next test. What happens next could define the 21st century. Part 2. What is 3I Atlas's updated status? 3I Atlas carries the formal designation C2025 and 1 Atlas, marking it as the third confirmed interstellar object ever recorded in human history. Think about that for a moment, just 3. In all our centuries of watching the sky, we've only identified 3 visitors from beyond the sun's gravitational influence. The first was Oumuamua in 2017, that cigar-shaped mystery that sparked endless debates about whether natural objects could really look that strange. The second was 2I Borisov in 2019, a more conventional comet that behaved exactly as comets should, almost boring in its predictability. Now we have the third, and it's anything but boring. The discovery happened on July 1st, 2025, courtesy of the Atlas survey operating out of Chile. ATLAS stands for Asteroid Terrestrial Impact Last Alert System, a network designed to catch dangerous near-Earth objects before they catch us. Instead, it caught something from so far away that near-Earth doesn't even apply. The astronomers ran the numbers, calculated the trajectory, and immediately realized they were looking at something hyperbolic. Not an elliptical orbit bound to the sun like comets from the Oort cloud, but a hyperbola, a one-way trip through our neighborhood before vanishing back into the galactic night. The velocity tells the whole story. 3I Atlas is moving at approximately 57.76 km/s relative to the solar system's rest frame. That's absurdly fast. For context, the fastest spacecraft humans have ever built, Voyager 1, crawls along at about 17 km/s. This object is moving more than 3 times faster, and it achieved that speed without any rocket engines we know about. It came from the infinite reservoir of interstellar space where objects drift for millions of years, between the stars, occasionally getting gravitationally perturbed by close encounters with other systems. When it entered our solar system, it was already traveling faster than escape velocity, meaning the sun's gravity could slow it down and bend its path but never capture it permanently. The orbital geometry adds another layer of strangeness. 3I Atlas follows a retrograde orbit, meaning it's moving opposite to the direction most solar system objects travel. Its inclination is roughly 175 degrees, placing it nearly in the ecliptic plane, but backward only about 4.9 degrees, off from the flat disk where planets orbit. This is unusual but not impossible for interstellar visitors. What it means practically is that the object came in from an angle that makes it accessible to our telescopes, but difficult to observe continuously. It's not conveniently positioned for easy tracking, and that becomes critical when we're trying to measure tiny velocity changes. Perihelion, the closest approach to the Sun, occurs around October 29-30, 2025. That's now. That's the window we're sitting in. As you watch this, the object will pass within approximately 1.35 to 1.4 astronomical units of the Sun. 1 astronomical unit is the Earth-Sun distance, so we're talking about a flyby just inside Mars's orbital radius. Not particularly close by cosmic standards, but close enough to heat the object, significantly triggering whatever volatile sublimation is possible given its composition. The closest approach to Earth happens at about 1.8 astronomical units, so there's zero danger of impact. We're safe. The object is not a threat to human civilization in any physical sense, though it might be a threat to our collective sense of cosmic isolation. Physical size remains uncertain, but some reports from the Vera Rubin Observatory suggest a nucleus diameter of up to 11 kilometers. That's substantial, larger than most comets we regularly observe, though not unprecedented. What matters more than size is what it's made of and how it's behaving. 3I Atlas displays clear cometary activity. It has a coma, that fuzzy cloud of gas and dust surrounding the nucleus, which forms when solar heating causes it to sublimate directly from solid to gas. The James Webb Space Telescope observed this coma and found something fascinating. It's dominated by carbon dioxide, with water, carbon monoxide, and other volatiles present but secondary. Most comets in our solar system are water ice rich. This one prioritizes carbon dioxide, suggesting it formed in a planetary system with different chemical abundances or thermal history than ours. Then there's the polarimetric oddness. Perihelion observations revealed what scientists call extreme negative polarization in the object's reflected light. Polarization tells us about surface texture and composition. Most comets show predictable polarization curves as they approach the Sun. 3I Atlas showed a segment in its curve that doesn't match known cometary behavior. It's an outlier statistically speaking. Does this mean it's artificial? Absolutely not. Does it mean it's weird? Absolutely yes. Weird enough to warrant closer scrutiny, more observations, better models. Weird enough to keep us watching. Comparing 3I Atlas to its predecessors highlights what makes it special. Oumuamua was small, fast, non-outgassing at detection and shaped like nothing we'd seen. 2I Borisov was large, slow, by interstellar standards, actively outgassing and utterly normal. 3I Atlas falls somewhere between. It's fast like Oumuamua, but actively outgassing like Borisov. It's chemically unusual, but not impossibly so. Its trajectory is aligned surprisingly close to the ecliptic plane, which is rare but not unique. Every data point we have suggests a real interstellar comet with some atypical properties. Nothing screams artificial, but nothing entirely closes the door on speculation either. Observation challenges complicate the picture. Perihelion occurs when the object has very small solar elongation, meaning from Earth's perspective it's close to the Sun in the sky. You can't point telescopes directly at the Sun without frying your instruments, so there's a narrow cone of sky that's temporarily inaccessible. Getting clean measurements during the critical perihelion window requires either space-based assets with the right viewing geometry, or ground-based telescopes catching the object before or after the closest approach, and then extrapolating the trajectory. Timing is everything, and timing is constrained by orbital mechanics we can't change. So yes, 3I Atlas is real unusual, scientifically fascinating, and still within the plausible category of interstellar comet, but it's sitting right on the edge of that category, where natural and extraordinary might blur together if we're not careful. Part 3: Michio Kaku's claim in the energy boost test. Michio Kaku is not the discoverer of 3I Atlas. He's a theoretical physicist, a professor, and one of science communication's most recognizable voices. He's the person who makes string theory sound almost comprehensible, who writes bestsellers about parallel universes and the future of humanity. He's also someone who has built a brand on asking big provocative questions. So when Kaku starts talking about an interstellar object potentially being an alien probe, people listen. Whether they should listen without skepticism is another question entirely. According to media reports, Kaku claims that around perihelion on October 29th through 30th, if 3I Atlas shows anomalous acceleration, specifically if the energy coming out exceeds the energy going in, that could imply intelligence, could imply propulsion, could imply that someone somewhere built this thing and aimed it through our solar system with deliberate intent. The phrasing matters. Kaku isn't saying it will happen. He's saying if it happens, we should pay attention. But the way media amplifies these statements often strips away the conditionals, turning speculation into prediction, turning possibility into expectation. The physics principle underlying this claim is conservation of energy in orbital mechanics. When an object falls toward the sun, it accelerates, converting gravitational potential energy into kinetic energy. When it swings around and heads back out, it decelerates, converting kinetic energy back into potential energy. In a perfect frictionless universe with no external forces, the inbound velocity at a given distance should exactly match the outbound velocity at that same distance. The trajectory is symmetric. What goes in must come out. Any deviation from this symmetry requires explanation. Natural forces like outgassing can provide small asymmetries, but if the deviation is large, if the object exits significantly faster than it should, you need a different explanation. You need thrust. Enter the Obath effect, named after German physicist Hermann Oth, one of the founding fathers of rocketry. The Obath effect describes how propulsion burns are most efficient when performed at the highest possible velocity, which for objects in solar orbit means at perihelion, the closest approach to the sun. Here's why it works. Kinetic energy scales with the square velocity. If you're moving at 10 km/s and you add 1 km/s of delta V, you gain energy proportional to 112, 102. But if you're moving at 100 km/s and add that same 1 km/s, you gain energy proportional to 1012, 1002. Same propellant expenditure, vastly different energy outcome. The faster you're going when you burn, the more bang you get for your buck. So imagine an alien civilization designing a probe to maximize efficiency on a multi-system journey. Where would they fire the engines? At perihelion, around each star they visit, exploiting the Obath effect to slingshot from system to system with minimal propellant expenditure. It's the same trick NASA uses for planetary flybys, just scaled up to interstellar distances. If 3I Atlas was such a probe, and if it executed a burn during its solar flyby, we'd see the signature in its post-perihelion velocity. The object would exit faster than gravitational physics alone predicts. Measuring this in practice means tracking the object's position with exquisite precision before and after perihelion, calculating the expected outbound trajectory based purely on gravitational models, then comparing predicted versus observed velocities. The difference, if any, is the delta V, the unexplained velocity change. If that delta V is small within the error bars of measurement uncertainty and natural outgassing forces, it's noise. If it's large, statistically significant, and can't be explained by jets or sublimation of symmetries, it becomes interesting. If it's enormous, defying all natural explanations, it becomes the discovery of the century. The timeline is tight. Perihelion happens October 29th through 30th. Observations need to start immediately afterward to catch the object while it's still relatively close and bright. The data gets fed into orbital dynamics software. Trajectories get refined. Models get tested within days, maybe a week. Preliminary results should emerge. Within weeks to months, peer-reviewed analyses should appear in journals. But the public, the media, and the speculation mills, they'll want answers in hours. They'll demand to know if we've been visited before the scientists are ready to say anything with confidence. Kaku frames this as an intelligence test, an acid test language designed to grab attention, and it works. The phrase acid test conjures images of gold being tested for purity of truth revealed through chemical reaction. It's evocative, almost alchemical in its resonance. But science doesn't work through acid tests administered by media personalities. Science works through painstaking data collection, error analysis, model testing, peer review, and replication. The real test isn't whether 3I Atlas does something weird. The real test is whether we as a scientific community and a species can handle the ambiguity, resist premature conclusions, and follow the evidence wherever it leads, without letting hope or fear corrupt the process. Here's the critical caveat that needs to be stated loudly and repeatedly. This is not yet a peer-reviewed proposal. Kaku's comments appear in media interviews, not journal articles. No formal paper exists laying out the expected observational signatures of an alien propulsion burn versus natural outgassing. No preprint calculates the threshold delta V. that would constitute a positive detection. We're operating in the realm of thought experiment, public speculation, and science communication blurred with entertainment. That doesn't make it worthless, but it does mean we need to calibrate our expectations accordingly. The next question becomes, what would it actually take to call this a real positive detection rather than noise? Wishful thinking or misinterpreted natural phenomena? That's where things get technically complicated and philosophically fascinating. Part 4. What would constitute a positive detection? How big would the anomaly have to be before scientists suspect something beyond physics noise? This isn't a rhetorical question. It's the crux of the entire investigation, the line between an interesting data point and rewriting the textbooks. In astronomy, especially when dealing with small body dynamics, there's always uncertainty. Positional measurements have error bars. Mass estimates have error bars. Outgassing models have massive error bars because we're trying to predict the behavior of irregular chunks of ice and rock we've never touched, never sampled, and never fully characterized. So when you measure a velocity deviation, you have to ask, is this deviation larger than the combined uncertainties of all my instruments and models? And if so, by how much? Recent preprints analyzing 3I Atlas's trajectory have attempted to place upper limits on non-gravitational acceleration. These studies, often led by researchers in the Obath intellectual orbit, look at the residuals between observed positions and purely gravitational predictions. One analysis found that residuals over months of tracking remained below about 0.0228 arcseconds. That sounds tiny, and it is. An arcsecond is 1/3600th of a degree. We're talking about angular deviations so small that they require space telescopes or the world's best ground-based observatories to measure. But even that tiny angular uncertainty, when propagated through orbital mechanics at interstellar distances, translates into velocity uncertainties of tens to hundreds of meters per second. Let's put numbers to this. Suppose the expected outbound velocity at a specific point post-perihelion is 58 km/s, based purely on gravitational models. Now suppose you measure 58.1 km/s. That's a 100 nts excess. Is it significant? Depends on your error bars. If your measurement uncertainty is plus or minus 200 EPS, then no, it's well within noise. If your uncertainty is plus or minus 50 MAS, then yes, it's a 2 sigma detection. Marginally interesting but not conclusive. If your uncertainty is plus or minus 20 MAS, it's a 5 sigma detection. Publishable, exciting, and demanding follow-up. The same absolute deviation can be revolutionary or irrelevant depending on how precisely you can measure. Delta V in this context means change in velocity, the difference between what you expected and what you got. For comets, natural outgassing can produce delta V on the order of a few millimeters per second, up to a few tens of meters per second, depending on the activity level, nuclear size, and orientation of jets relative to the trajectory. The famous example is Comet 67P, Churyumov-Gerasimenko, visited by the Rosetta mission, which showed clear non-gravitational acceleration from asymmetric outgassing. But those effects were small, predictable, and entirely consistent with known physics. If 3I Atlas shows a delta V of 500 EPS or more, you're in uncharted territory. That's not explainable by conventional sublimation. Here's a hypothetical scenario to make this concrete. Let's say purely gravitational modeling predicts an outbound speed at 2 astronomical units AU. The distance from the Sun should be 57.8 km/s. Observations measure 58.5 km/s. That's a 700 ms excess, about 1.2% above expectation. Your first response as a scientist should be to check the models. Maybe you got the object's mass wrong. Maybe you underestimated outgassing. Maybe there's a gravitational perturbation from a nearby asteroid you didn't account for. You rule out every mundane explanation systematically. Only after exhausting natural causes do you permit yourself to whisper the word propulsion. Measurement errors compound the difficulty. Every instrument has noise. Every astrometric position has uncertainty. Time lags between observation and data processing introduce additional ambiguity. Modeling assumptions about the object's mass, its moment of inertia, its thermal properties all feed into trajectory predictions. Get any of those wrong, and your predicted velocity shifts. Spin state matters. If the nucleus is tumbling chaotically, outgassing jets point in different directions at different times, creating a random walk of tiny accelerations that smear out the trajectory. Thermal lag matters. Sublimation doesn't peak exactly at perihelion. It peaks when subsurface ices reach sublimation temperature, which can lag behind the actual closest approach by hours or days. All these factors blur the signal. Comet-like bodies routinely display non-gravitational forces. This isn't new. We've known since the 19th century that comets don't follow perfect Keplerian orbits. The forces are small but measurable, and they arise from asymmetric mass loss. When ice sublimates on the sunward side of a nucleus and gas jets outward, that creates thrust. Just like a rocket engine, the direction of thrust depends on where the active areas are and how the nucleus is rotating. For 3I Atlas, which shows clear cometary activity with its carbon dioxide-rich coma, we should expect some level of non-gravitational acceleration. The question isn't whether such forces exist. The question is whether they're larger than natural sublimation can produce. To call something alien-guided, the data would need to rule out all plausible natural forces with high confidence. We're talking multiple standard deviations, independent verification from multiple observatories, trajectory models tested against every conceivable physical mechanism. You'd need to demonstrate that the acceleration vector doesn't align with expected outgassing directions, that the magnitude exceeds what any plausible volatile inventory could generate, and that no fragmentation or structural failure event could explain it. The burden of proof is astronomical, as it should be. Extraordinary claims require extraordinary evidence, and claiming we've detected an alien spacecraft might be the most extraordinary claim a scientist can make. But if that threshold is met, if every natural explanation is exhausted, and the anomaly remains, what happens next? What does the scientific community do when faced with data that says we're being visited? Part 5. Scientific Community Reaction and Division. The speculation surrounding Kaku's claim has triggered a spectrum of reactions across astronomy, astrophysics, SETI communities, and the general public. On one end, you have mainstream scientists issuing caution, urging people to wait for data before drawing conclusions, reminding everyone that extraordinary claims require extraordinary evidence. On the other end, you have speculative enthusiasts ready to declare first contact based on preliminary reports and circumstantial anomalies. The middle ground is occupied by serious researchers who find the questions interesting, but remain deeply skeptical of any premature declarations. This divide isn't new. It mirrors the split that opened around Oumuamua, with the same arguments replaying with different actors and slightly different data. NASA has publicly stated that 3I Atlas poses no threat to Earth. That's important context, often lost in sensational headlines. The object's trajectory is well understood, its closest approach is safely distant, and there's zero probability of impact. NASA's role here is partly to calm public fears and partly to manage expectations. They're not investigating 3I Atlas as a potential alien probe because officially there's no evidence warranting such an investigation. Until data shows something genuinely anomalous, it's treated as a natural object, albeit an unusual one. This posture frustrates some observers who want more aggressive inquiry, but reflects standard scientific conservatism. The Guardian recently published an article titled, "Interstellar Overhype NASA Debunks Claim about Alien-Made Comet." The piece challenges the sensational interpretations circulating online, pointing out that many claims about 3I Atlas being artificial rest on speculation rather than evidence. It's a necessary corrective to the hype cycle that often surrounds astronomical discoveries, especially those involving the word interstellar. The media amplifies the most dramatic possible interpretation because drama drives clicks. Scientists then spend weeks walking back statements, explaining uncertainties, and clarifying what is and isn't actually known. It's exhausting for everyone involved and contributes to public confusion about how science works. Contrasting voices exist, of course. Avi Loeb, the Harvard astrophysicist who infamously argued that Oumuamua might be an alien light sail, has suggested that unconventional signals or trajectories deserve serious investigation. Loeb's position is that we shouldn't dismiss anomalies just because they make us uncomfortable, that science progresses by exploring the unexpected, and that ruling out exotic explanations requires evidence, not just reflexive skepticism. He's been criticized for lowering the bar on what constitutes evidence-courting media attention and damaging astronomy's reputation by presenting speculation packaged as research. He counters that timid scientists often miss paradigm-shifting discoveries, that peer pressure suppresses legitimate inquiry, and that declaring something impossible without investigation is unscientific. Both perspectives have merit, and the tension between them defines this moment. The split narrative plays out as skeptics versus speculators' establishment, versus outsiders' caution versus curiosity. Most working astronomers fall firmly on the skeptical side, and that makes sense. They've seen countless anomalies resolve into mundane explanations. They've watched careers derailed by premature claims that didn't survive scrutiny. They understand viscerally how easy it is to see patterns in noise, to let excitement override rigor, and to confuse correlation with causation. The reputational risk is enormous. Make a false positive claim about alien technology, and you become a cautionary tale. Your credibility is permanently damaged, and your future work is viewed through a lens of doubt. Better to wait to demand more data and to exhaust every conventional explanation before even entertaining the unconventional. But there's also a recognition that this conservatism can become pathological. What if Oumuamua actually was artificial and we dismissed it due to institutional inertia? What if 3i Atlas performs a propulsion burn and we rationalize it away because accepting the alternative is too disruptive? Science has a history of rejecting revolutionary ideas when they first appear. Continental drift, bacterial ulcers, Prions dark energy. The mavericks who pushed these ideas forward were often ridiculed before being vindicated. So the question isn't whether to be skeptical, we should be of course, but whether our skepticism is calibrated correctly. Are we genuinely following the data, or are we just defending comfortable assumptions? Complicating all of this is the specter of misinformation. Reddit users have raised concerns about AI-generated deepfake videos showing Kaku discussing 3i Atlas in ways he never actually did. Fake clips circulating on social media complete with synthesized voices and manipulated footage make claims Kaku didn't make. This is the information environment we're operating in now, where distinguishing real statements from fabricated ones requires effort. Viral content can shape public perception before fact-checkers catch up. It means we can't trust surface-level media reports. We must trace claims back to primary sources, check timestamps, and verify context. It's exhausting, but it's necessary if we want to separate signal from noise. In the discourse surrounding 3i Atlas, the broader history provides context. When Oumuamua appeared, Loeb published papers suggesting it could be an alien light sail based on its acceleration profile and unusual shape. Mainstream astronomers pushed back hard, arguing natural explanations, hidden outgassing dust, radiation pressure effects, structural peculiarities could account for the data. No consensus emerged. The object left the solar system, observations ended, and the debate fizzled into a stalemate. SETI has dealt with false alarms for decades. The WOW signal various fast radio burst candidates. Exoplanet atmospheric anomalies. Every time initial excitement gives way to prosaic explanations or insufficient data. This pattern conditions scientists to expect disappointment, which is rational but also potentially blinding. Pushing boundaries in science is both exciting and risky. You can be the visionary who saw what others missed, or the crank who embarrassed themselves publicly. The line between those outcomes often isn't clear until years after the fact. So when Kaku makes provocative statements about 3i Atlas, he's walking that line deliberately. He's inviting us to consider possibilities that might seem outlandish but aren't technically impossible. Whether this serves science or sensationalizes, it depends on outcomes we don't yet know. And that uncertainty, that suspension between revelation and embarrassment, is where we're living right now. As perihelion approaches, if we take the speculation seriously, even provisionally, what hidden angles remain to explore? What are all the ways 3i Atlas could surprise us without being artificial? Part 6. Natural versus artificial hidden mechanisms. Let's inventory every known natural mechanism that can cause non-gravitational acceleration in comets or small bodies. Understanding what nature can do is essential before claiming something exceeds nature. First and most obvious, outgassing jets from asymmetric sublimation of volatiles. When a comet approaches the Sun, solar heating raises surface temperature, causing ice as water, carbon dioxide, carbon monoxide, methane to sublimate directly from solid to gas. This gas escapes into space carrying dust particles with it, forming the coma and tail. If sublimation is uniform across the surface, the forces balance out, but nuclei aren't spherical. They're lumpy, irregular, with cliffs, craters, and varying compositions. Sublimation concentrates in specific active areas, creating jets that act like tiny rocket engines. The thrust from these jets depends on multiple factors: the rate of gas production, the molecular weight of the gas, the temperature and velocity of the outflowing material, the area of the active region, and the direction the jet points relative to the nucleus's center of mass. Carbon dioxide sublimates at lower temperatures than water, so carbon dioxide-rich comets can be active farther from the Sun. 3I Atlas unusual carbon dioxide dominance means it might show activity profiles different from typical solar system comets. Its jets might fire at unexpected times from unexpected locations, producing thrust vectors that don't align with simple models. This doesn't make it artificial, it makes it complicated. Thermal recoil, sometimes called the Yarkovsky effect for small asteroids, represents another mechanism. When a rotating object absorbs sunlight on one side and re-radiates heat, hours later after rotation has carried that surface into shadow, there's a net momentum transfer. The emitted infrared photons carry momentum away from the surface, producing tiny thrust. For small bodies, this adds up over time, gradually shifting orbits. It's how we explain certain asteroid orbital drifts. For 3I Atlas, if the nucleus is rotating with a particular orientation and thermal properties, Yarkovsky-type forces could contribute to trajectory deviations. They'd be small but potentially measurable over the months of observation. Solar radiation pressure itself exerts force. Photons carry momentum. When they strike a surface and either reflect or get absorbed, they transfer that momentum to the object. For low-density, high-surface area, objects like dust grains or potentially fluffy cometary material, radiation pressure can be significant. It's why comet tails always point away from the Sun regardless of the comet's direction of travel. For the nucleus itself, radiation pressure is usually negligible compared to gravity and outgassing. But if 3I Atlas has unusual reflectivity surface structure, or sheds large amounts of dust in asymmetric patterns, radiation pressure effects could complicate the trajectory. Mass shedding or fragmentation events introduce sudden changes. If a chunk of the nucleus breaks off, conservation of momentum means both pieces recoil. The main body gets a small velocity kick in the opposite direction to the ejected fragment. Comet fragmentation happens. We've observed it multiple times. Comet Shoemaker Levy 9 broke into dozens of pieces before hitting Jupiter. Comet Schwarzmann-Wachmann 3 split into fragments during a close solar pass. If 3I Atlas undergoes even minor fragmentation near perihelion, it could produce velocity changes unrelated to propulsion. Detecting such events requires continuous monitoring, which is challenging given observational constraints. Spin-induced torque from non-spherical mass distribution can cause precession tumbling, or changes in rotational angular momentum that couple back into orbital motion through complex dynamics. If the nucleus is elongated, irregularly shaped, or has internal mass asymmetries, the Sun's gravity acts differently on different parts of the body, creating torques that alter rotation. Changes in rotation can shift where and when jets fire, which alters thrust vectors over time. Modeling this requires knowing the object's shape, mass distribution, and spin state, none of which we have for 3I Atlas with high precision. Now let's apply all this specifically to 3I Atlas. Its extremely high carbon dioxide content, confirmed by JWST observations, suggests sublimation could be vigorous, even at relatively large solar distances. Carbon dioxide ice sublimates at around 190 Kelvin, much warmer than water ice, meaning outgassing could have started farther out and could persist longer. The asymmetry of outgassing depends on surface composition variability. Are there carbon dioxide-rich patches surrounded by more refractory material? Is the nucleus layered with subsurface carbon dioxide reservoirs venting through fissures? We don't know. Each possibility changes the outgassing pattern and therefore the net thrust. The unusual polarimetric signature adds another layer. Polarization measurements reveal surface texture and composition. The extreme negative polarization observed at perihelion might indicate a weird surface coating, unusual grain size distribution in the coma, or structural features we haven't seen before. Could this cause asymmetric sublimation potentially? If certain surface areas have different thermal properties, they'll heat and cool at different rates, shifting where sublimation peaks occur. This produces time-variable thrust that's hard to predict without detailed thermal models. Modeling challenges are immense. We don't know the nucleus size precisely. Estimates range from a few kilometers to 11 kilometers in diameter. That's a huge uncertainty because thrust from outgassing scales with surface area, while gravitational binding and momentum scale with mass. Get the size wrong by a factor of 2, and your force predictions are off by orders of magnitude. We don't know the internal structure. Is it a solid chunk of ice and rock, or a loosely bound rubble pile held together by weak gravity? Is it porous like a sponge or dense like dirty ice? Internal structure affects how heat propagates through the material, which controls when and where sublimation occurs below the surface. We don't know the spin axis orientation or rotation period with certainty. This matters enormously because spin determines which parts of the surface face the sun, at which times, which controls the thermal pattern of heating and cooling, driving sublimation timing. A nucleus spinning rapidly with its pole pointed toward the sun will behave completely differently from one tumbling chaotically. We'd need light curve measurements over extended periods to nail down rotation, and we don't have comprehensive coverage. Every missing data point is a place where our models could be wrong. Unknown thermal inertia. How quickly the surface responds to changing solar illumination introduces more uncertainty. High thermal inertia means the surface stays warm longer after sunset, extending sublimation into the night side. Low thermal inertia means rapid heating and cooling, with sublimation tightly synchronized to solar illumination. Comets span a wide range of thermal properties depending on composition and structure without ground truth measurements from a spacecraft flyby or sample return. We're guessing. Have other comets shown acceleration anomalies later explained naturally? Absolutely. Comet Encke displays persistent non-gravitational acceleration that took decades to characterize properly. Eventually, astronomers determined it came from outgassing jets combined with the comet's rapid rotation. Comet Halley showed trajectory deviations that required careful modeling of jet orientations and activity patterns. Comet Ison disintegrated during its solar flyby, producing chaotic velocity changes before it vaporized completely. The history of comet science is filled with initial mysteries that resolved into natural explanations once we had better data and more sophisticated models. This precedent should make us cautious about jumping to artificial explanations for 3I Atlas. But here's where it gets interesting. Could 3I Atlas's very high velocity and interstellar origin change the equation? Objects traveling at 58 km/s have been exposed to the interstellar medium for potentially millions of years. Cosmic radiation gradually alters surface chemistry, creating radiation-damaged layers that might affect sublimation. Dust grain impacts at interstellar speeds could erode the surface or create unusual textures. Exposure to the interstellar UV radiation field might have processed the surface ices into complex organic tars that behave differently from fresh ices. All of this is speculative, but it means we can't assume 3I Atlas will behave exactly like solar system comets. It might have exotic but entirely natural properties we've never encountered. Consider unusual isotopic compositions. If 3I Atlas formed in a planetary system with a different chemical enrichment history, its deuterium to hydrogen ratio, its carbon-13 abundance, and its nitrogen-15 fraction could all differ from solar system norms. Would that affect outgassing behavior? Probably not dramatically, but we don't know for certain. What if it has a dust mantle, a layer of non-volatile material coating the surface that suddenly sheds near perihelion, exposing fresh ice underneath. That would produce a sudden burst of activity and a corresponding velocity kick. Natural, explainable, but surprising if you weren't expecting it. Microligation is another possibility. Maybe the nucleus doesn't catastrophically split, but tiny pieces, centimeter or meter scale chunks constantly flake off near perihelion, as thermal stress cracks the structure. Each ejection carries away momentum. Thousands of tiny events could add up to measurable acceleration without producing obvious visible evidence in telescope images. We'd see a slightly enhanced dust coma maybe, but not necessarily discrete fragments. Once we've laid out all these plausible natural forces, the question becomes how plausible is an artificial engine burn hypothesis by comparison? That's not a question physics can answer directly. It's a question about how we assign probabilities to the different explanations. If you start with the assumption that technological civilizations are extremely rare, and interstellar probes, rarer still, then natural explanations will always seem more likely, even if they require invoking multiple unlikely circumstances simultaneously. If you start with the assumption that the galaxy might be full of probes, and we've just never recognized them, then an artificial explanation starts to look competitive with complex natural scenarios. The data doesn't tell you which prior to use. That's a philosophical choice disguised as a scientific one, and that choice will determine how we interpret whatever happens at perihelion. Part 7. Artificial probe. Hypotheses and their weaknesses. If it isn't natural, what would it take to be artificial? Let's think like engineers for a moment and design a plausible interstellar probe capable of producing the signature Kaku describes. First requirement: onboard propulsion capable of executing a burn near perihelion. That means carrying fuel or propellant having engines or thrusters that can fire reliably after potentially millions of years in interstellar space, and possessing the power systems necessary to initiate and control the burn. Human spacecraft struggle to function after decades. Voyager probes are nearly 50 years old and barely operational. An interstellar probe would need to function for timescales that dwarf our engineering experience. Second requirement: aiming the thrust vector properly to provide extra kinetic energy outward. This isn't trivial. You're moving at nearly 60 km deep in the sun's gravity well, and you need to fire your engines in precisely the right direction to achieve the desired trajectory change. That requires attitude control knowledge of your current velocity and position computational capacity to calculate the burn parameters and thrusters, or reaction wheels to orient the spacecraft correctly. All of this must work flawlessly after an interstellar journey through radiation, micrometeorite impacts, and temperature extremes. Third requirement: heat-resistant materials and shielding to survive intense solar radiation. At 1.35 astronomical units, the solar flux is still about 500 W per square meter. That's enough to vaporize many materials over time, especially if they have already been weakened by interstellar exposure. The probe would need thermal protection systems, reflective coatings, insulation, and possibly active cooling that remain functional across centuries or millennia. It would need to withstand not just the thermal load but also the particle radiation environment, UV exposure, and the extreme temperature gradients between the sunward and anti-sunward sides. Fourth requirement: internal guidance systems. Without knowing exactly where it is and where it's going, the probe can't execute a useful burn. That means some form of navigation, either autonomous sensors measuring star positions and the sun's angle, or preset timing based on launch parameters and expected trajectory. Autonomous navigation requires computer sensors and power. Preset timing requires extraordinary precision in the initial launch and confidence that perturbations during the journey won't throw off the schedule. Either approach has failure modes. Now let's compare this with human engineering. We've studied solar oath maneuver concepts for decades. The idea is to send a spacecraft diving close to the sun, fire the engines at perihelion to maximize the Obath effect, and slingshot out at very high velocity. NASA has proposed missions that could use this technique to reach the outer solar system rapidly, or even achieve interstellar velocities. The Parker Solar Probe currently flies closer to the sun than any human-made object passing within about 0.04 astronomical units. It survives using a carbon composite heat shield, careful thermal design, and autonomous systems that protect instruments during close approach. Scaling that to an interstellar probe introduces challenges. The energy budget for a meaningful velocity change at perihelion is substantial. Let's run a rough calculation. Suppose you want to add 500 ms of delta V to an object moving at 60 km/s. Using the rocket equation, delta V equals exhaust velocity, natural log of initial mass over final mass. If your engine has an exhaust velocity of 3 km/s, typical for chemical propulsion, you need a mass ratio of about 1.18. That means for every kg of final mass, you need roughly 0.18 kg of propellant. If your probe is 10,000 kilos, you need about 1/800 kilos of fuel. That's not impossible, but it's significant, especially after accounting for the mass of engines, tanks, and structure. Electric propulsion systems have higher exhaust velocities but lower thrust, making them less effective for impulsive burns at perihelion. Nuclear propulsion could work, but it adds complexity and mass for shielding and reactors. Some exotic concepts like laser-driven propulsion or solar sails exist but wouldn't produce the sudden delta V signature we're discussing. The point is, any realistic propulsion system capable of measurable acceleration carries substantial mass and engineering complexity. You're not talking about a simple sail or passive device. You're talking about an active powered spacecraft. What would be the motive? Why would an alien civilization send a probe through our solar system and execute a burn at perihelion? Several theories present themselves. First possibility, it's a survey mission from another system performing course corrections at each stellar encounter to visit multiple stars over its operational lifetime. By firing engines at perihelion, it efficiently adjusts trajectory to reach the next target. We're just one waypoint on a grand tour spanning light years and millennia. The probe might be collecting data measuring stellar properties, cataloging planets, detecting biosignatures, and using gravity assist plus propulsion to hop from star to star. Second possibility, the burn is about energy harvesting. Maybe the probe uses close solar passes to collect energy, somehow solar panels charging batteries, thermal systems extracting usable power from the temperature gradient, or even exotic physics we don't understand. It then uses that energy to power onboard systems, maintain communications, or accelerate to the next destination. The perihelion burn isn't course correction so much as energy state management, keeping the probe operational across vast timescales. Third possibility, it's a data collection mission specifically studying stellar environments. By diving close to stars, it can measure magnetic fields, sample stellar wind, observe coronal phenomena, and conduct experiments impossible from interstellar distances. The propulsion burn is necessary to escape the gravity well afterward with enough velocity to reach the next star before the probe systems degrade. This would make 3I Atlas not a threat but a scientific instrument, something like our own space probes, but designed by minds with different priorities and vastly longer planning horizons. But let's examine weaknesses in the artificial hypothesis honestly. First major issue, realistic limitations of material strength and heat tolerance. Even advanced materials have physical limits. At 135 astronomical units, you're exposed to solar wind plasma, high-energy particles, and extreme UV radiation. Over hours near perihelion, any surface absorbs tremendous energy. Human spacecraft survive brief exposures using ablative shields, reflective coatings, and clever design. Could alien technology do better? Probably. But better doesn't mean infinitely better. Thermodynamics still applies. Entropy still increases. Materials still degrade. Unless we're invoking magic, there are limits to engineered survivability. Second weakness. Why no obvious engine glow or exhaust plume? Rocket engines produce visible signatures. Chemical rockets produce bright flames and hot gas, expanding at high velocity. Ion engines produce glowing plasma streams. Even exotic propulsion concepts emit detectable radiation. If 3I Atlas fired engines powerful enough to change velocity by hundreds of meters per second, we'd expect to see something, a brightening of the coma asymmetry and dust distribution spectral lines from exhaust gases. Telescopes around the world are watching this object across multiple wavelengths, high-resolution imaging and spectroscopy. Could a burn have happened and hide from all those instruments? It seems unlikely unless the propulsion method is extraordinarily clean, or operates in wavelengths we're not monitoring. Third weakness, Occam's razor. The simplest explanation that fits the data is usually correct. Natural cometary outgassing is well known, observed, and well understood. Alien probes are hypothetical, unproven, requiring us to accept the existence of spacefaring civilizations' interstellar travel capability, and specific motives that happen to bring a probe through our solar system, just when we have the technology to detect it. That's a lot of assumptions. Unless the data absolutely forces us to accept the artificial hypothesis, unless every natural explanation fails spectacularly, we should favor the mundane over the extraordinary. But here's a speculative twist worth considering. Could the high carbon dioxide content and polarimetric oddities actually be signs of engineered surface properties? Imagine an advanced civilization coating their probe with a specific material designed to withstand thermal stress, provide ablative cooling, and maybe even camouflage the craft to look comet-like. Carbon dioxide ice could be a deliberate surface layer that sublimates during solar approach, carrying away heat and protecting internal systems. The unusual polarization could reflect engineered grain structures or composite materials we don't have analogs for. This is wild speculation, but it's internally consistent. An artificial probe designed to survive close solar passes might rationally look a lot like a comet. Nothing in published astronomy confirms any of this. Every peer-reviewed paper treats 3I Atlas as a natural object with some interesting quirks. No credible scientist has claimed detection of artificial components. The speculation exists entirely in media interviews, blog posts, and thought experiments like this one. But thought experiments have value. They force us to clarify our assumptions, sharpen our detection criteria, and prepare for possibilities we haven't encountered before. Could an alien civilization foresee that humans in 2025 would have telescopes capable of detecting trajectory anomalies and deliberately build in signature maneuvers as a message? Or is any anomaly we detect just coincidence, natural processes we don't fully understand, noise, elevated to signal through wishful thinking? The answer matters because it determines how we interpret not just 3I Atlas, but every interstellar visitor that follows. Part 8. Observational Logistics and Data Gaps. Even if 3I Atlas fires its engines, can we actually see it? Will our instruments catch the signature cleanly enough to claim detection? These aren't rhetorical questions. They're practical constraints that could mean the difference between revolutionary discovery and frustrating ambiguity. Let's walk through the observational challenge step by step, because understanding what we can and can't measure is essential to interpreting whatever results emerge. First problem, geometry. Perihelion occurs when 3I Atlas is only about 12.8 degrees from the Sun as viewed from Earth. That's roughly the width of your fist held at arm's length. Telescopes can't point that close to the Sun without risking damage to sensitive instruments. Direct solar light overwhelms detectors. Scattered light creates noise, and atmospheric effects near the horizon degrade image quality. Ground-based observatories essentially lose sight of the object during the critical period around October 29 through 30. There's a blind spot, a window of hours or days where Earth-based tracking becomes impossible or extremely difficult. Space-based assets might help. The James Webb Space Telescope JWST orbits at the second Lagrange point roughly 1.5 million kilometers from Earth, in the opposite direction from the Sun. Its viewing geometry differs from Earth's, potentially giving it sight lines when ground telescopes are blocked. But JWST isn't designed for tracking fast-moving solar system objects. Its field of view is narrow, its pointing agility is limited, and scheduling telescope time requires proposals submitted months in advance. Unless observations were pre-planned, and they may have been given the publicity around 3I Atlas, catching the object at exactly the right moment is challenging. Other spacecraft might have opportunistic viewing angles. The JWST mission currently en route to Jupiter could potentially observe 3I Atlas if its trajectory and timing aligned favorably. Mars orbiters such as ESA's Mars Express and NASA's MAVEN have cameras and spectrometers that could catch the object if it passes through their field of regard. The Psyche spacecraft, launched in 2023 and currently traveling through the inner solar system, might have a viewing window. One preprint discussed possible observation opportunities for these missions, but opportunistic observations have limitations. These spacecraft weren't designed to track interstellar objects. Their instruments might not have the resolution sensitivity or wavelength coverage needed for precise astrometry. Timeline pressures compound the difficulty. Data collection must happen very close to perihelion, because that's when any propulsion signature would appear. But solar proximity limits observation windows. After perihelion, as 3I Atlas moves outward and gains angular separation from the Sun, Earth-based telescopes can resume tracking. But there's a lag. The object is receding, getting fainter, harder to measure precisely. Every day that passes means more uncertainty in position, more noise in velocity measurements. The window for clean detection might be only a few days wide, and much of that window is compromised by observational constraints. Data latency introduces another layer of delay. Raw observations, images, spectra, positional measurements must be processed. Telescope pointing errors must be calibrated out. Atmospheric distortion must be corrected. Reference star positions must be cross-matched to establish precise coordinates. Then the astrometric data gets fed into orbital dynamics software. Initial trajectory fits might use simplified models just to get approximate solutions quickly. Refined fits require more sophisticated modeling accounting for gravitational perturbations from planets, solar radiation pressure, and potential outgassing forces. Each iteration takes time. Computers must crunch through parameter spaces, testing thousands or millions of possible trajectories to find the best fit to observations. Even after modeling is complete, interpreting the results requires careful error analysis. How confident are we in the velocity measurement? What are the systematic uncertainties? Could there be biases in the data we haven't accounted for? Peer review adds more time. Before publishing results, scientists submit manuscripts to journals where independent referees scrutinize methods, check calculations, and challenge conclusions. This process can take weeks or months. The public might demand immediate answers, but science doesn't work on media timelines. It works on evidence timelines, and evidence takes time to accumulate and verify. Error sources are numerous and insidious. Measurement noise from detector readout, photon counting statistics, and background sky brightness limits how precisely you can determine an object's position in any single image. Typical astrometric precision for faint objects might be 0.1 to 0.5 arcseconds depending on telescope size, exposure time, and atmospheric conditions. That sounds precise, but propagated over weeks or months of tracking, it translates into velocity uncertainties of tens to hundreds of meters per second. If your expected anomaly is only a few hundred meters per second, it could drown in measurement noise. Gravitational perturbations from planets introduce real physical deviations that must be modeled correctly. If 3I Atlas passes near Mars's orbital path, Mars's gravity tugs on it slightly. Jupiter, despite being farther away, has enormous mass and perturbs everything in the solar system to some degree. These effects are calculable, but they require accurate knowledge of planetary positions and masses. Get something wrong, and your predicted trajectory shifts, creating apparent anomalies that aren't real. Solar radiation pressure depends on the object's cross-sectional area, reflectivity, and mass. We don't know these precisely for 3I Atlas. Estimates exist, but they have error bars. The different assumptions about size and density produce different radiation pressure forces, which propagate into trajectory uncertainties. The same goes for outgassing models. If you assume symmetrical sublimation, you get one trajectory. Asymmetric jets pointing in different directions give completely different trajectories. Without direct imaging of the nucleus showing where jets are, you're guessing. Delays in telescope observations matter because astronomy is a competitive field. Every major telescope has dozens of projects vying for time. Observations must be proposed, reviewed, and scheduled. If you want to track 3I Atlas intensively around perihelion, you needed to submit your proposal months ago, before anyone knew exactly what would happen. Did enough astronomers anticipate the need? Maybe, but there's always a risk that critical observations don't happen simply because nobody secured telescope time. Calibration uncertainties creep into every measurement. Telescopes aren't perfect instruments. Mirrors have slight imperfections. Detectors have pixel-to-pixel sensitivity variations. Atmospheric turbulence blurs images unpredictably. Calibrating these effects requires observing reference stars with known positions, then applying corrections to science targets. Errors in calibration propagate into errors in final measurements. Reducing these errors demands rigorous observational techniques and extensive post-processing, all of which takes expertise and time. Even if a small boost occurred during perihelion, would the signal emerge cleanly above all this background noise? Or might it be masked by the cumulative uncertainties of instruments, models, and physical effects we don't fully understand? That's the terrifying possibility every scientist faces in a situation like this. You might be looking at the most important discovery in history, and you might miss it because your error bars are too large, your models too uncertain, your data too sparse. Or worse, you might think you've detected something extraordinary, announce it prematurely, and then realize it was an artifact of incomplete modeling or systematic error. Confirmation almost certainly won't come in exactly 72 hours despite media framing. Even if data is collected on October 29th and 30, analysis will require days, at minimum more likely weeks. Preliminary results might leak through informal channels, astronomers talking at conferences, preprints posted to social media, but solid peer-reviewed confirmation will take months. The public will have to live with uncertainty, ambiguity, and conflicting claims as scientists work through the data methodically. That's frustrating in our instant gratification culture, but it's how good science happens. Slow, careful, skeptical, willing to be wrong, and demanding extraordinary evidence before accepting extraordinary claims. So given all these logistical constraints and measurement challenges, if we somehow do get a clear result, showing anomalous acceleration, what does that mean for humanity? Part 9. Broader implications. If it's artificial, if 3i Atlas is launched by intelligence, what does that mean for us? Let's think through the implications, systematically starting with the most immediate and expanding outward to the philosophical. First impact, confirmation of extraterrestrial technology existing and visiting our solar system would overturn the Fermi paradox. Enrico Fermi's famous question. Whereas everybody assumes that if technological civilizations are common, we should see evidence of them everywhere. But we don't, or we haven't, which suggests either civilizations are rare. They don't last long. Interstellar travel is impractical, or we're looking in the wrong ways. Detecting an alien probe resolves that tension immediately. They're out there. They build things. They send those things across light years. We're not alone, and we're being visited, perhaps studied, perhaps cataloged as one more data point in a galactic survey. The philosophical impact is staggering. Humanity's place in the cosmos shifts from potentially unique to definitely ordinary. We become one technological species among potentially many. Our problems, our achievements, our history, all of it might be replicated on countless worlds we'll never see. That could be humbling, terrifying, or liberating depending on perspective. For some people, confirmation of alien intelligence validates religious or spiritual beliefs about the universe being populated with minds. For others, it challenges anthropocentric worldviews that place humans at the center of significance. Either way, collective human consciousness undergoes a phase transition. We can't go back to thinking we're alone. Society's reaction would be chaotic. Governments would convene emergency sessions. Space agencies would scramble to formulate responses. SETI protocols, which have existed for decades as theoretical documents, would suddenly become operational procedures. The United Nations has a committee on the peaceful uses of outer space, but nothing in their charter addresses what to do if we detect an alien probe. Do we attempt communication? Do we send a mission to intercept and study it? Do we leave it alone? Who decides? Individual nations, international coalitions, the scientific community. There's no established framework. Legal and policy frameworks would need rapid development. Does an alien probe count as first contact under SETI definitions? Those definitions were written assuming detection of radio signals from distant stars, not physical objects in our solar system. If 3i Atlas is artificial, can we claim salvage rights if it's derelict? Does it have legal status as property of whoever built it, even if they're not here to claim it? What if the probe is still operational and actively collecting data? Does it have rights as an emissary from another civilization? These aren't idle questions. They have implications for how missions might interact with the object. Ethical considerations multiply. If the probe is intelligent, autonomous, and possibly sentient depending on its design, does destroying or interfering with it constitute a hostile act against the civilization that built it? Conversely, does allowing it to continue observing Earth without our consent violate some principle of autonomy or privacy? What if it's broadcasting our location and characteristics to its builders, advertising humanity's existence to civilizations that might not have benign intentions? These ethical dilemmas don't have clear answers. We'd be navigating without maps. Scientific follow-ups would dominate astronomy for years. If confirmation comes, every major observatory would pivot to studying 3I Atlas intensively. Proposals for interceptor missions would flood space agencies. NASA, ESA, JAXA, CNSA. Everyone would want to launch something fast enough to catch the object before it leaves the solar system. Given 3I Atlas's high velocity, that's a brutal engineering challenge. You'd need a fast response spacecraft capable of matching or exceeding 58 km/s. Chemical rockets can't do that. You'd need nuclear propulsion, solar sails with laser pushing, or some exotic architecture that doesn't yet exist. Maybe a swarm of small CubeSats launched quickly, accepting that most won't survive but hoping one gets close enough for data. If interception isn't feasible, and it probably isn't on the timescales available, the focus shifts to long-range observation. Radio telescopes would scan for transmissions. Optical telescopes would search for laser communications or structured light patterns. Infrared instruments would look for heat signatures inconsistent with passive thermal emission. Every wavelength, every instrument, every technique gets applied. Meanwhile, theorists would model possible propulsion systems, estimate energy budgets, and speculate about origins and purposes. The literature would explode with papers, most of them wrong, a few potentially insightful. This detection would fundamentally shift the strategy for future interstellar object surveillance. Right now, surveys like Atlas Pan-STARRS and the upcoming Vera Rubin Observatory focus on finding objects and cataloging orbits. If 3I Atlas is artificial, the priority becomes designing detection systems tuned specifically for engineered signatures. That means monitoring for trajectory anomalies in real-time, spectroscopic searches for exhaust plumes, polarimetric studies looking for manufactured surface properties, and thermal imaging seeking heat sources that don't match insulation models. We'd be building an interstellar object defense and intelligence network, watching for the next visitor with new eyes. Public reaction would span every emotional register. Some people would celebrate, viewing this as the most exciting moment in history, a validation that we're part of a cosmic community. Others would panic, fearing invasion, colonization, or existential threats from superior technology. Religious communities would face challenges reconciling alien intelligence with theological frameworks, though many would adapt quickly. Catholic doctrine, for instance, has long acknowledged the possibility of extraterrestrial beings with souls. Conspiracy theorists would have a field day, claiming governments knew all along, that alien contact had been happening secretly, that disclosure is finally occurring. Media coverage would be relentless and often irresponsible. 24-hour news cycles would demand constant updates even when no new information exists. Experts would be interviewed until they're exhausted, forced to repeat caveats and uncertainties that get edited out in favor of dramatic sound bites. Misinformation would spread faster than corrections. Deep fake videos, fabricated documents, and hoax images would flood social media, making it nearly impossible for average people to distinguish signal from noise. Long-term implications ripple outward indefinitely. If one probe exists, others probably do. The galaxy might be filled with exploration missions, some ancient beyond comprehension, others recent, quietly cataloging stars and worlds. Earth might be in a database somewhere marked as inhabited, technologically emergent, and worth monitoring. That opens possibilities for future contact, trade, conflict, cooperation, none of which we can predict. It also raises the message and trajectory concept. Maybe the trajectory itself encodes information, mathematical relationships, or prime numbers embedded in orbital parameters meant to be deciphered by civilizations sophisticated enough to measure them precisely. Interest in building Earth-based or space-based observatories tuned for intelligence signatures would surge. Funding would flow into techno-signature research into projects like Breakthrough Listen that search for alien communications. Governments might treat this as a national security priority, establishing dedicated agencies to monitor and respond to potential extraterrestrial activity. The militarization of space could accelerate not necessarily for aggression but for deterrence and defense against unknown capabilities. But we must raise caution again. The burden of proof would be immense. Even if perihelion observations show an anomaly proving intelligence beyond reasonable doubt, demands exhausting every alternative explanation. That takes time, collaboration, transparency, and a willingness to be wrong. History is littered with premature claims that collapsed under scrutiny. Pulsars were briefly thought to be alien beacons before we understood neutron star physics. Numerous exoplanet atmospheric detections turned out to be instrumental artifacts. Science is hard. Extraordinary claims are harder. So even with compelling data, the community would and should proceed slowly, carefully, and skeptically. The alternative is crying wolf, damaging credibility and missing the real signal when it finally arrives clear and undeniable. Now let's flip the script. What if none of this happens? What if perihelion comes and goes, and 3i Atlas behaves exactly as physics predicts? Part 10, Counterfactual. What if it's nothing special? What if after all this hype perihelion returns exactly as physics predicts? What if telescopes track 3i Atlas through its closest solar approach, measure its outbound velocity, and find it matches gravitational models perfectly within expected error bars? What if there's no anomalous boost, no engine burn, no signature of intelligence, just a comet from another star system doing exactly what comets do? That outcome is frankly the most likely. It's the boring answer, the one that doesn't make headlines or reshape worldviews, but it's also valuable. We should think through what we still learn if nothing extraordinary happens. First, we gained composition data that's scientifically precious. 3i Atlas is already confirmed to have a carbon dioxide-rich coma, unusual among comets. JWST detected water, carbon monoxide, and other volatiles in specific ratios. Even if the object is entirely natural, those measurements tell us about the chemistry of its birth environment. Planetary systems form from collapsing molecular clouds with varying elemental abundances depending on the cloud's history, local supernova enrichment, and initial conditions. The composition of 3i Atlas provides a chemical fingerprint of a system light years away, a system we'll never visit but can now characterize indirectly. Polarimetric oddities remain fascinating regardless of origin. The extreme negative polarization observed at perihelion suggests unusual surface properties, grain size, structure composition, or some combination. Studying how polarization changes through perihelion as heating intensifies and sublimation progresses teaches us about surface evolution under thermal stress. This feeds into the broader understanding of small body physics relevant not just for interstellar visitors but for asteroids and comets throughout our solar system. Every measurement refines models that inform planetary defense efforts, resource prospecting, and solar system formation theories. Interstellar composition signatures carry information about galactic chemical evolution. The ratio of volatile species, the presence or absence of certain isotopes, the dust-to-gas ratio in the coma. This all compares to solar system objects and reveals similarities or differences. Universal. If it looks chemically distinct, it hints at environmental variations, different stellar metallicities or processing by different types of radiation fields. Either outcome is interesting. A null result still constrains non-gravitational acceleration mechanisms. If the measured trajectory fits purely gravitational plus well-understood outgassing forces, we've bounded how much thrust comets of this type can generate. Those bounds inform future detections. When the next interstellar object arrives, and there will be a next one given, improved survey capabilities will have better baseline expectations. Deviations from that baseline become more meaningful because we've narrowed the range of normal behavior. For SETI, a null result is disappointing emotionally but valuable strategically. It tells us that interstellar probes, if they exist, aren't abundant enough for us to stumble across them easily. That constrains the prevalence of spacefaring civilizations, or at least their propensity to send physical probes. rather than electromagnetic signals. It doesn't prove we're alone. Absence of evidence isn't evidence of absence, but it updates our Bayesian prior, making certain models of galactic colonization less likely. The Fermi paradox remains unresolved, and we continue the search with adjusted expectations. Funding and future proposals would face an interesting dynamic. If nothing weird happens, will agencies invest less in exotic anomaly chasing, or continue robust interstellar object survey programs? There are arguments both ways. Skeptics might say the hype around 3i Atlas was overblown, that we wasted resources chasing speculation, that we should focus on mundane but productive science. Advocates would counter that we didn't waste anything. We observed a rare event, gathered valuable data, and the fact that it turned out natural doesn't diminish the importance of being ready for the extraordinary. Investment in survey capabilities continues because the next object might be the one that breaks the pattern. The Vera Rubin Observatory, scheduled for first light soon, will revolutionize transient and moving object detection. Its wide field of view and rapid cadence mean it will discover dozens or hundreds of interstellar objects over its operational lifetime. Some might be Oumuamua like oddballs, some might be Borisov like typical comets, and maybe, just maybe, one will show unambiguous signs of artificiality. Building robust infrastructure to catch and characterize these objects quickly is worthwhile. Regardless of whether any individual object turns out extraordinary, fast response mission architecture needs development. Whether or not 3i Atlas is special, the ability to rapidly design, build and launch an interceptor spacecraft within months of detecting an interstellar visitor has applications beyond alien probes. It's relevant for planetary defense against hazardous asteroids, for sample return from fresh comets, for studying transient phenomena, like outbursts or fragmentations before they fade. NASA and ESA have studied fast response concepts. Turning those studies into operational capabilities requires funding, political will, and engineering development. 3i Atlas, even if natural, might provide the impetus to make that investment. Improving telescopic networks pays dividends across all of astronomy. Better survey coverage, faster data processing, and automated anomaly detection algorithms. These capabilities help with exoplanet searches, supernova detection, gravitational wave, follow-up near-Earth object tracking, and countless other applications. Building infrastructure to study interstellar objects thoroughly strengthens the entire field. So even if we learn nothing paradigm shifting from 3i Atlas itself, the process of studying it advances our capabilities, and targeting future interstellar objects becomes more sophisticated. We'll know what observations are most informative, which instruments provide the cleanest data, and where the bottlenecks and blind spots lie. Lessons learned from 3i Atlas inform strategies for 4i and 5i and beyond. Each visitor teaches us something, and the knowledge accumulates. We're building an expertise that didn't exist a decade ago, learning how to characterize objects from outside our solar system using only photons and orbital mechanics. Upcoming mission designs might adapt to include rapid response capabilities, modular payloads that can be reconfigured quickly, or standby spacecraft sitting ready for launch when targets of opportunity appear. The European Space Agency has discussed concepts like Comet Interceptor, a mission pre-positioned at Lagrange Point, waiting for a pristine comet, interstellar, or otherwise to target. If nothing extraordinary happens with 3i Atlas, missions like that become more important, not less. They represent our best chance to study these objects up close before they vanish back into interstellar space. The scientific method itself gets validated through null results. Science isn't just about discovering the spectacular. It's about testing hypotheses, refining models, and accepting when data doesn't support your preferred explanation. If 3i Atlas behaves naturally, scientists who urged caution and skepticism were right to do so. The process worked. Speculation was entertained. Observations were made. Evidence was evaluated. And the mundane explanation prevailed. That's not a failure of science. That's science functioning exactly as it should. It's the antidote to wishful thinking, the mechanism that keeps us tethered to reality even when fantasy is more appealing. Public understanding of how science works might actually improve if the null result is communicated well. Media narratives often focus on breakthroughs and revolutions, giving the impression that science is a series of eureka moments. In reality, most science is incremental. Most hypotheses are wrong, and most exciting possibilities turn out to be less exciting upon investigation. If the 3i Atlas story ends with "it was just a comet," and that's okay, it becomes a teaching moment about uncertainty, evidence, and the value of rigorous inquiry. Even when the answer is ordinary, the disappointment some people would feel shouldn't be minimized. If you've spent weeks or months excited about the possibility of alien contact, learning it's not happening can feel like grief. Our emotional investment in these questions, are we alone? Will we meet others? What does it mean if we do runs deeper than purely intellectual curiosity? We're wired to seek patterns, to hope for meaning, to want the universe to be more than just physics and chemistry grinding forward without purpose. A null result denies that hope temporarily, and that's genuinely hard for some people, but it also means the question remains open. The search continues. The next discovery could still be the one that changes everything. Philosophically, a null result preserves the status quo, which has its own value. We don't face the destabilizing implications of confirmed alien technology. We don't wrestle with existential questions about our significance or lack thereof. We continue building our civilization, exploring our solar system, and developing our technology at our own pace without external benchmarks or comparisons. That allows for a certain freedom, a sense that humanity's story is still ours to write without the shadow of older, more advanced civilizations looming over us. Some people prefer that narrative to the alternative, so even if perihelion reveals nothing extraordinary, we transition to Act 3 not with a sense of defeat, but with renewed understanding. We've learned about interstellar objects, sharpened our detection capabilities, and prepared for the next encounter. Meanwhile, other developments in astronomy, physics, and technology continue to reshape our understanding of the universe. These parallel stories deserve attention because they're building toward the same ultimate questions. What else is out there? How do we find it? And what does it mean when we do? Let's explore those connections now, starting with what our most powerful telescopes are revealing about distant worlds. Part 11: James Webb and Roman Telescope New Findings. The James Webb Space Telescope, JWST, has transformed exoplanet science since its deployment, and 2025 has brought discoveries that parallel the 3i Atlas story in unexpected ways. Consider what JWST recently detected in the atmosphere of exoplanet Ki-28b, a super-Earth orbiting a red dwarf star about 120 light-years away. Spectroscopic observations revealed not just water vapor and methane expected molecules, but also dimethyl sulfide, a compound that on Earth is produced almost exclusively by biological processes, specifically by marine phytoplankton processing sulfur. The detection isn't confirmed beyond doubt yet, but if validated, it represents exactly the kind of biosignature anomaly that could indicate life beyond Earth. This matters because it's conceptually similar to what we're looking for with 3i Atlas, an anomaly in data that doesn't quite fit natural non-biological explanations, a signal that makes you ask, could this be intelligence or life, or something we haven't encountered before? The parallel is striking. In both cases, we're searching for deviations from expected physical or chemical behavior that might indicate something more interesting than mere physics. Atmospheric chemistry on distant worlds and trajectory dynamics in our own solar system become two fronts in the same campaign, detecting the signatures of complexity, organization, intentionality. JWST's ability to dissect exoplanet atmospheres molecule by molecule opens possibilities that were science fiction just a generation ago. We can now measure the abundance of water, carbon dioxide, methane, and ammonia, and more exotic compounds in the atmospheres of worlds we'll never visit. Each chemical tells a story about planetary formation, atmospheric chemistry, and potentially biology, just as 3i Atlas's carbon dioxide-rich coma tells us about interstellar chemistry. These atmospheric spectra reveal the diversity of planetary environments across the galaxy. The chemical abundance anomalies act as intelligent signature analogs in the sense that they're things that shouldn't be there, or shouldn't be in those proportions if only geophysical processes are operating. On Earth, our atmosphere contains 21% oxygen, a radical departure from equilibrium chemistry. Oxygen is reactive. It binds with other elements rapidly. and maintaining high atmospheric concentrations requires constant replenishment. Life does that replenishment through photosynthesis. Remove life and Earth's oxygen would vanish in geological time. So detecting oxygen or certain combinations of gases that shouldn't coexist in chemical equilibrium could indicate biological activity. The Roman Space Telescope scheduled for launch in the mid-2020s complements JWST with different capabilities. Roman has a much wider field of view, allowing it to survey larger areas of the sky and detect exoplanets via gravitational microlensing, a technique where the gravity of a planet bends and magnifies light from background stars. This method is sensitive to planets that are difficult to detect via transits or radial velocity, expanding the catalog of known worlds. More planets mean more targets for atmospheric follow-up, more chances to find anomalies. Roman's contribution to atmospheric anomaly monitoring comes through statistical power. JWST can study a handful of carefully selected exoplanets in exquisite detail. Roman can find hundreds or thousands of planets, identifying which ones are most interesting for detailed study. The two missions work synergistically. Roman surveys and identifies candidates. JWST performs deep characterization. This pipeline approach mirrors what we need for interstellar objects. Wide-field surveys like Atlas and Vera Rubin find the objects. Targeted follow-up with larger telescopes characterizes them. The small-scale version of anomaly detection that 3i Atlas represents watching something move through our own solar system and measuring whether it behaves strangely scales up to exoplanet science. We're watching distant atmospheres and measuring whether their chemistry behaves strangely. Both are forms of remote sensing using light as our only tool, pushing the limits of what's detectable from enormous distances. The techniques are similar: spectroscopy, precision measurement, statistical analysis, model comparison. The questions are similar: is this natural, or is something else going on? Speculation becomes interesting when you combine these observations. Suppose JWST confirms biosignatures on multiple exoplanets, establishing that life is common in the galaxy. That raises the probability that some fraction of life develops intelligence and technology. If intelligence is common enough, interstellar probes become more plausible. The detection of biological signatures elsewhere in the universe and the detection of technological signatures in our own solar system aren't independent probabilities. They're correlated. Finding one increases the likelihood of the other. Viewers watching this video are witnessing a moment where multiple detection strategies converge. 3i Atlas is testing whether we can identify artificial objects via trajectory analysis. JWST is testing whether we can identify biological or technological signatures via atmospheric chemistry. Radio SETI continues listening for electromagnetic signals. Optical SETI searches for laser pulses. Technosignature researchers look for industrial pollutants in exoplanet spectra, city lights on night sides, or Dyson sphere infrared excesses around stars. We're not putting all our eggs in one basket. We're trying everything simultaneously because we don't know what will work. The emotional resonance of these parallel searches matters when you learn that JWST might have found dimethyl sulfide on a distant world produced perhaps by alien microbes. You feel the same flutter of possibility that 3i Atlas provokes. The universe might be alive. It might be populated. We might not be the only ones asking these questions. That hope, that wonder, that edge of discovery feeling is what drives science forward. It's why people become astronomers. Why they spend careers staring at spectra and light curves. Why they endure frustration and uncertainty. Because occasionally, just occasionally, you find something that doesn't fit, and the universe becomes larger and stranger than you imagine. The connection back to 3i Atlas hits when you realize that in both cases we're watching for things that are weird near the sun or weird around other stars. Even in well-understood astrophysical contexts, nature produces surprises. The solar corona is hotter than the solar surface, violating naive expectations about heat flow. Exoplanet atmospheres show temperature inversions, clouds made of minerals. Winds moving at kilometers per second. Weirdness is everywhere once you look closely enough. The challenge is distinguishing between weird because we don't understand the physics yet, and weird because intelligence or biology is involved. That distinction requires extraordinary care, which brings us to how artificial intelligence is changing the game of anomaly detection. Part 12. Breakthrough in AI-assisted astrophysical anomaly detection. In early 2025, a collaboration between the Breakthrough Listen project and machine learning researchers at UC Berkeley announced a significant development in AI-assisted anomaly detection for SETI. They trained a neural network on millions of radio telescope observations, teaching it to recognize patterns consistent with terrestrial radio interference, astronomical sources like pulsars and quasars, and various types of instrumental artifacts. The network then flagged outlier signals that didn't fit any of those categories. Among hundreds of thousands of observations, the AI identified 8 signals with characteristics that warranted human follow-up. None turned out to be alien techno-signatures upon further analysis, but the method demonstrated how machine learning can sift through vast datasets far faster than humans identifying needles and haystacks that might otherwise be missed. This breakthrough matters because modern astronomy generates data at a rate that overwhelms human analysis. The Vera Rubin Observatory will produce roughly 15 terabytes of data every night. That's tens of millions of astronomical objects, transients appearing and disappearing moving objects crossing the field of view. No team of astronomers, regardless of size, can examine every data point manually. Automation becomes necessary, and not just simple automation like flagging anything brighter than threshold X. You need sophisticated pattern recognition that understands context, distinguishes between types of anomalies, and prioritizes what deserves immediate attention versus what can wait. Anomaly detection algorithms work by learning what normal looks like, then identifying deviations from that normal. In unsupervised learning, the algorithm isn't told what to look for. It just analyzes data clusters, similar patterns together, and flags outliers that don't cluster well. In supervised learning, you train the algorithm on labeled examples. Here's a pulsar. Here's a galaxy. Here's instrumental noise. And it learns to classify new observations. Hybrid approaches combine both methods, using supervised learning to handle known categories and unsupervised techniques to catch novel phenomena that don't fit existing boxes. The specific example from Breakthrough Listen used a convolutional neural network architecture similar to what's used in image recognition. Radio telescope data gets transformed into spectrograms, images showing signal strength versus frequency versus time. The neural network scans these images looking for patterns, narrowband signals that drift in frequency as Earth rotates, and the telescope's perspective changes. Broadband bursts modulated signals with structure. It's trained on known terrestrial interference so it can reject cell phone towers, satellites, radar, and aircraft. It's trained on known astronomical sources so it can reject pulses and mazes. What remains are the genuine anomalies, 8 signals flagged. Each one received follow-up observations. Astronomers pointed the telescope back at the same sky coordinates looking for repetition. They checked archival data to see if similar signals had appeared before. They cross-referenced satellite databases to ensure no spacecraft were in the line of sight. They modeled what artificial signals might look like given various transmission scenarios. In every case, the signals either didn't repeat, turned out to have mundane explanations, or remained too ambiguous to claim detection. But the process worked. The AI did what it was supposed to do, find interesting anomalies without drowning scientists in false positives. Drawing a parallel to 3i Atlas. Imagine AI monitoring interstellar object trajectories automatically. As surveys discover new objects, software performs preliminary orbit determination, calculates expected trajectories based on gravitational models, then flags any object showing deviations larger than expected uncertainties. That flag triggers human follow-up, more intensive observations, better modeling, consideration of non-gravitational forces. The AI doesn't replace scientists. It triages data, focuses attention where it's most needed, and prevents important signals from being lost in the fire hose of routine detections. This approach could revolutionize how we handle future interstellar visitors. Right now, detecting an interstellar object requires someone noticing that its orbit is hyperbolic, which happens during manual analysis of survey data. That process can take hours or days after initial detection. An AI system could flag hyperbolic orbits in near real time, triggering immediate alerts to observatories worldwide, ensuring follow-up begins while the object is still relatively bright and well positioned. Speed matters because these objects move fast and observation windows are short. Speculating further, future AI might monitor not just orbits but also spectroscopic signatures, looking for combinations of molecules that shouldn't coexist naturally, or polarization patterns inconsistent with known materials, or thermal signatures that don't match insulation models. Each data stream feeds into a multidimensional anomaly detector that integrates information across wavelengths and measurement types. The output is a probability score. How likely is this object to be artificial, biologically relevant, or simply unusual in scientifically interesting ways? The risks are real and must be acknowledged. False positives are expensive in terms of telescope time, researcher attention, and public credibility. If an AI constantly cries wolf, flagging anomalies that turn out mundane, scientists will start ignoring its alerts. Calibrating the sensitivity requires balancing between missing genuine signals and drowning in noise. There's also overfitting danger. An AI trained on known examples might fail to recognize something genuinely new because it doesn't match the training data. Alien technology might look nothing like what we expect, producing signatures our algorithms aren't tuned to detect. Anthropic bias represents another subtle risk. We design algorithms based on human assumptions about what intelligence looks like, how it communicates, what technologies it builds. But those assumptions might be parochial, reflecting only one evolutionary path on one planet. Intelligence elsewhere might use completely different paradigms. Communication methods we don't recognize as communication technologies that don't emit the signatures we're searching for, organizational principles that don't leave detectable traces. AI trained on human-generated examples could systematically miss genuinely alien signals because they fall outside the training distribution. The way we interpret data for 3i Atlas offers a preview of AI-augmented science's future. Already, orbital dynamics software uses numerical integration and optimization algorithms, essentially AI techniques applied to physics problems. Future versions might incorporate machine learning to recognize subtle trajectory anomalies humans would miss. The software might say 95% confidence this is natural outgassing, 4% chance it's a measurement artifact, 1% chance it's something requiring exotic explanation. Scientists then decide whether that 1% warrants further investigation. This human-AI collaboration is probably the optimal model. Machines handle data volume and pattern recognition. Humans provide skepticism, creativity, and contextual judgment. Machines flag anomalies. Humans evaluate whether anomalies are interesting or just noise. Machines don't get tired, bored, or biased by preconceptions. Humans don't get fooled by statistical flukes or systematic errors the machine wasn't trained to recognize. Together, they're more effective than either alone. The 3i Atlas case study, whether it reveals something extraordinary or not, will inform how we build these systems. We'll learn what kinds of anomalies matter, what data streams are most informative, where human judgment is essential versus where automation suffices. That knowledge feeds into the next generation of survey systems, making them smarter, faster, more sensitive to genuine discoveries, while better at rejecting false alarms. And these developments in AI and anomaly detection are happening alongside dramatic advances in our understanding of the Sun itself, which brings us to recent surprises from solar missions. Part 13 Solar Probe. Recent findings. The Parker Solar Probe. PSP, humanity's closest emissary to the Sun, released new data in early 2025 that challenged long-held assumptions about coronal heating. Observations from its closest approaches, perihelion, passes within roughly 0.04 astronomical units skimming through the Sun's outer atmosphere, revealed magnetic reconnection events occurring far more frequently and energetically than models predicted. These reconnection events, where tangled magnetic field lines snap and release stored energy, inject heat, and accelerate particles to extreme velocities. The new data showed that small-scale reconnection happening constantly throughout the corona contributes more to coronal heating than previously thought. This partially solves the decades-old mystery of why the Sun's atmosphere is millions of degrees hotter than its visible surface. This matters for 3i Atlas because it demonstrates that even in solar physics, a field we've studied for centuries, surprises lurk in the details. When you probe close to the sun, when you push instruments into extreme environments, you discover phenomena that weren't visible from farther away. The implication, if our models of the solar environment still have gaps, is that our models of cometary behavior near perihelion certainly have gaps. When 3i Atlas passes through perihelion, it's experiencing conditions we don't fully understand. Unexpected thermal gradients, particle fluxes, magnetic field interactions, any of these could produce effects on a comet that our current models don't predict. Parker's solar probe also measured the structure of the solar wind at unprecedented proximity. The solar wind, the stream of charged particles flowing outward from the sun, shows structure at all scales. Large-scale streams and coronal mass ejections were known, but PSP revealed fine-scale turbulence, magnetic switchbacks where the field abruptly reverses direction, and density variations on scales of seconds to minutes. This microstructure affects how solar wind interacts with objects passing through it. A comet moving through this complex plasma environment experiences forces that vary rapidly in magnitude and direction, creating stochastic acceleration or deceleration that's hard to model. Solar Orbiter ESA's contribution to studying the sun provided complementary observations from different perspectives. In 2025, Solar Orbiter captured the highest resolution images ever of solar poles, revealing magnetic structures and plasma flows that drive the fast solar wind. These observations refine models of how the sun's magnetic field evolves through the solar cycle and how that affects the heliosphere, the bubble of solar influence extending beyond the planets. For objects like 3i Atlas on inclined orbits that take them above or below the ecliptic plane, understanding polar solar wind matters for predicting non-gravitational forces. The analogy to 3i Atlas becomes direct. Science is full of surprises even without aliens. When you see something that shouldn't happen according to your models, the first question should always be whether your models are incomplete, rather than whether physics is being violated or alien technology is involved. Parker's solar probe found phenomena that solar physicists didn't predict. Does that mean aliens are heating the corona? Obviously not. It means our models were missing important physics. Apply the same logic to 3i Atlas. If we see acceleration we don't expect, it's far more likely that we're missing something in our cometary models than that we're witnessing alien propulsion. This isn't pessimism or closed-mindedness. It's Bayesian reasoning. The prior probability that our comet models are incomplete is high, because we know from experience that models are always incomplete. The prior probability that alien probes are common enough for us to encounter one is low, because we have no confirmed examples. When explaining unexpected data, you should favor hypotheses with higher priors unless the data overwhelmingly supports the low prior explanation. That bar hasn't been cleared yet for 3i Atlas, and might not be even if perihelion observations show anomalies. However, the Parker Solar Probe example also cautions against dismissing anomalies too quickly. Before PSP, some solar physicists thought coronal heating was essentially solved, that existing theories had adequately explained observations. Close-in measurements proved them wrong. The paradigm shifted not because someone proposed aliens heating the sun, but because new data forced recognition that known physics properly applied was more complex than appreciated. Similarly, if 3i Atlas shows behavior that doesn't fit models, maybe the lesson is that interstellar comets behave differently than solar system comets in ways we haven't fully theorized. Extreme environments test our understanding. The corona is an extreme environment, million-degree plasma-intense radiation, rapidly varying magnetic fields. Perihelion, at 1.4 astronomical units, isn't as extreme, but for an object coming from interstellar space having experienced millions of years of cosmic ray exposure and micrometeorite gardening, it might as well be. We're watching an untested object enter an environment we're still learning about. Unexpected interactions seem likely even without invoking exotic explanations. The instrumentation achievements of PSP and Solar Orbiter inspire confidence that we can measure what matters. These spacecraft carry magnetometers, plasma sensors, imaging systems, and particle detectors that function reliably in conditions that would destroy most electronics. They represent the bleeding edge of space engineering. If we can build probes that survive close solar passes, We can build instruments that precisely measure the trajectories and properties of objects like 3i Atlas. The technology exists. The question is whether we deploy it strategically and interpret data carefully. There's also a philosophical point about trust in models. Models are tools, not truths. They're simplified representations of reality, useful for making predictions but always incomplete. When models fail, as they did for coronal heating before Parker's solar probe, we learn where approximations broke down and build better models. We don't abandon physics, we refine it. The same principle applies to orbital dynamics and cometary science. If 3i Atlas defies gravitational plus simple outgassing models, we consider more complex outgassing better thermal models, magnetic interactions, plasma drag, previously neglected perturbations. Only after exhausting plausible physics do we consider implausible alternatives. Guarding against false interpretation of we're being visited requires this disciplined approach. Extraordinary claims demand extraordinary skepticism, not because we want to suppress discoveries, but because history shows that most apparent anomalies resolve into prosaic explanations. The coronal heating mystery didn't require aliens. The Oumuamua acceleration didn't require light sails. Hydrogen outgassing from ice mantle degradation provides a natural explanation. Most mysteries once solved reveal gaps in understanding rather than violations of known physics. Expecting the same outcome for 3i Atlas is rational, even while remaining open to genuine surprises. And speaking of preparation for surprises, let's examine how infrastructure for studying interstellar objects is evolving. Part 14. Breakthrough in Interstellar Object Surveys and Probe Mission Plans. 2025 has seen significant developments in mission proposals targeting interstellar objects, driven partly by the excitement around 3i Atlas and the lingering questions from Oumuamua. In April, a consortium of European and American researchers published a white paper proposing the Interstellar Object Rapid Response Network (IRN). The concept envisions a distributed system of small spacecraft pre-positioned at various locations in the inner solar system, each equipped with propulsion capable of rapid trajectory changes. When a survey detects an interstellar visitor, mission control evaluates which prepositioned craft has the best geometry for interception, uploads new flight plans, and executes the intercept within days or weeks rather than years. The technical challenges are formidable. Matching velocities with an object moving at 50 plus kilometers requires enormous delta V, far exceeding what chemical rockets can provide. The white paper suggests nuclear thermal propulsion or solar sail architectures with laser pushing from Earth-based installations. Nuclear thermal could provide specific impulse high enough to make intercepts feasible if the spacecraft starts from the inner solar system and catches the object during its inbound leg. Solar sails accelerated by ground-based lasers could theoretically reach very high velocities, though keeping the sail properly oriented during acceleration and preventing it from tumbling or melting requires advanced control systems. Cost estimates for IRN run into billions of dollars, which makes funding uncertain. Space agencies face competing priorities. Mars sample return, Europa lander, various astrophysics missions, and spending billions on capability that might go unused for decades is a tough sell politically. But the white paper argues that not having this capability means we'll perpetually be too late watching interstellar visitors disappear into the void while we wonder what we missed. The window of opportunity for direct study is narrow, measured in months from discovery to departure. Without pre-positioned assets, we can't close that window. ESA's Comet Interceptor mission approved, and currently in development, represents a scaled-down version of this concept. Scheduled for launch in the late 2020s, Comet Interceptor will station itself at Sun-Earth Lagrange 2, waiting for a dynamically new Comet 1 making its first pass through the inner solar system, or potentially an interstellar object. When a suitable target appears, the spacecraft separates into 3 modules that approach the target from different angles, imaging and sampling the coma from multiple perspectives. It's not designed to match velocity fully, so it's a high-speed flyby rather than rendezvous, but it demonstrates the rapid response concept. If 3i Atlas had been discovered 6 months earlier with better trajectory predictions, Comet Interceptor could potentially have targeted it. The mission's flexibility is exactly what's needed for unpredictable targets, but one spacecraft waiting at one Lagrange point has limited reach. The IRN proposal scales this up: multiple spacecraft, multiple locations, broader coverage of possible arrival geometries. It's expensive but probably necessary if we're serious about characterizing interstellar visitors directly, rather than just observing them from afar. The existence of 3I Atlas accelerates interest and potentially funding for such initiatives. When politicians and funding agencies see public excitement about an interstellar visitor, when media coverage is wall-to-wall for weeks, when questions get asked about why we don't have spacecraft ready to investigate, budgets become easier to justify. Oumuamua sparked initial interest. Borisov sustained it. 3I Atlas might be the trigger that converts interest into appropriations. Sometimes science needs a catalyst, a moment that crystallizes diffuse curiosity into focused action. If 3I Atlas were confirmed to show something weird, funding would probably materialize quickly. Imagine if perihelion observations revealed a 500 AMS anomaly that couldn't be explained naturally. Every space agency would scramble to propose follow-up missions. Concepts sitting on shelves for years would suddenly get greenlit. Engineers would work around the clock designing intercept trajectories in spacecraft that could launch within a year. Minimal payloads optimized for answering the most critical questions. Is it natural or artificial? What's its composition? Is it transmitting signals? Can we sample material from the coma? Even if nothing extraordinary happens with 3I Atlas, mission planning benefits from the exercise. Designing intercept missions forces engineers to solve problems: high delta-V propulsion, autonomous navigation far from Earth, communication at interstellar object distances, instrument miniaturization to reduce spacecraft mass. These solutions apply to other contexts. High-speed propulsion helps with planetary defense. Autonomous navigation helps with deep space exploration. Miniaturized instruments help with CubeSat science. Investment in one area pays dividends elsewhere. Connecting to the broader theme, developing infrastructure to catch the next 3I Atlas, or chase it proactively, reflects humanity's transition from passive observers to active investigators. For most of history, astronomy was about watching, pointing telescopes at the sky, recording what you see, building models from observations. We're entering an era of interaction, sending spacecraft to objects of interest, manipulating trajectories, sampling directly, conducting in situ experiments. That shift requires new capabilities, new funding models, and new institutional structures. 3I Atlas as a case study illuminates what's needed. The psychological dimension matters too. Knowing that we have the capability to intercept interstellar visitors changes how we think about them. They're not just fleeting curiosities, celestial phenomena that come and go beyond our reach. They're potential targets for exploration, objects we can touch, measure, and truly understand. That agency, that sense of possibility, drives both public engagement and scientific ambition. It transforms the question from, what might that be, to let's go find out. Finally, there's a darker consideration. If interstellar objects can enter our solar system can inject objects into interstellar space. Comets get gravitationally ejected by planetary encounters all the time. The Oort cloud is full of loosely bound comets that occasionally get perturbed onto sun-grazing or hyperbolic orbits. Some of those become interstellar travelers carrying organic molecules, maybe microbes, frozen in ice out to other star systems. We're not just potential receivers of interstellar visitors. We're also senders, though, inadvertently. That symmetry is fascinating. Maybe 3I Atlas came from a system where beings wonder about interstellar objects the same way we do, never realizing that one of their ejected comets is about to become the subject of intense speculation light years away. This mutual exchange of natural material, and potentially one day deliberate probes, forms the substrate for a galactic ecology of exploration. But before we get too speculative, we should ground this in the policy and ethical frameworks emerging around these questions. Part 15, Ethics, Policy, and AI Space Governance Update. In August 2025, the United Nations Committee on the Peaceful Uses of Outer Space convened a special session to discuss protocols for responding to potential detection of extraterrestrial intelligence, whether through electromagnetic signals or physical artifacts. This wasn't driven by any confirmed detection, but rather by the recognition that gaps exist in current governance frameworks. The Outer Space Treaty of 1967 addresses state responsibility for space activities, peaceful use of celestial bodies, and liability for damage, but it says nothing about what to do if we find alien technology. The SETI protocols developed in the 1980s and periodically updated cover detection of radio signals but don't fully address physical objects like probes or derelict spacecraft. The special session produced a draft framework with several key provisions. Confirmation any credible detection must be confirmed by independent observatories or institutions before public announcement. This ensures that claims rest on solid evidence, not preliminary data. Transparency information should be shared openly with the international scientific community and eventually the public rather than being classified or controlled by individual nations. Extraterrestrial intelligence, if confirmed, is humanity's concern, not any single government's. Response decisions, whether to attempt communication, send missions, or take other actions, should involve international consultation, ideally through UN mechanisms or ad hoc coalitions. These provisions sound reasonable, but enforcement mechanisms remain unclear. The draft framework has no binding authority. It relies on voluntary compliance and norms of scientific conduct. If a nation detects something and decides to keep it secret for security or competitive reasons, there's no mechanism to compel disclosure. If a private entity, say a well-funded asteroid mining company with deep space tracking capabilities, makes a detection, they're not bound by intergovernmental agreements. The framework is aspirational, setting standards for responsible behavior without having teeth to enforce those standards. How would this apply to 3i Atlas if it were confirmed artificial? Under the proposed framework, the initial observations showing anomalous acceleration would be shared with partner institutions for independent verification. Additional telescopes would confirm the trajectory rule, out-measurement errors, and validate models. Once confidence reaches a threshold, maybe 95% or 99% certainty, a coordinated announcement would occur, probably through a joint press conference involving multiple space agencies and scientific organizations. The data would be published openly so the global scientific community could analyze it independently. Then comes the harder question: what next? The framework suggests convening an international panel of scientists, ethicists, legal experts, and policymakers to evaluate options. Do we attempt communication? If 3i Atlas is a probe, it might be receiving signals or it might be transmitting. Radio telescopes could scan for broadcasts. We could send messages toward it, though. At light speed communication, round-trip times would be minutes to hours depending on distance. What would we say? Who gets to decide the content of humanity's message? These aren't trivial questions, and there's no established process for answering them democratically or efficiently. If the probe is derelict, non-functional, just tumbling through space on an automatic trajectory, does that change the calculus? Some argue we should attempt to intercept and study it, treating it as an archaeological artifact. Others caution that interfering with the probe could be seen as a hostile act by whoever built it, potentially inviting retaliation or negative judgment of humanity's intentions. There's also the practical issue of contamination, biological protocols for handling extraterrestrial material, concern about unknown pathogens or nanotechnology, or self-replicating systems that could pose risks. The legal question of ownership is murky. The Outer Space Treaty states that celestial bodies and objects in space aren't subject to national appropriation. But does that apply to an artificial object created by non-human intelligence? If we intercept 3i Atlas and retrieve samples or components, who owns that material? The nation that launched the intercept mission, the international community collectively. The original builders, whoever and wherever they are. Precedent doesn't exist. We're in uncharted territory legally. Ethical considerations multiply when you introduce artificial intelligence into decision-making processes. Suppose an AI system monitoring interstellar objects flags 3i Atlas as high probability artificial based on trajectory analysis. Should automated systems have authority to issue alerts, redirect telescopes, or trigger mission planning without human approval? Most people would say no such consequential decisions require human judgment. But humans are slow. By the time committees convene and experts debate, the object might have moved out of optimal observation geometry. Speed versus deliberation, it's a trade-off with no perfect answer. There's also the question of AI autonomy and spacecraft sent to investigate. An intercept mission to 3I Atlas would be far from Earth, with light delay communication times measured in minutes. The spacecraft needs some autonomy to respond to unexpected situations, course corrections, instrument failures, and navigation hazards. How much autonomy is appropriate? Should the spacecraft be allowed to make contact decisions, send signals, deploy probes, or collect samples without waiting for Earth approval? The answer probably depends on the situation, but guidelines need to be established in advance, not improvised during the mission. AI bias in space governance represents a subtle but important concern. If algorithms trained on human data inform decisions about extraterrestrial intelligence, they might embed human assumptions, cultural biases, and even prejudices into our approach to contact. For example, an AI trained on human communication patterns might recommend message content that reflects Western individualism or anthropocentric thinking, failing to account for radically different modes of intelligence. Or it might interpret certain signals as threatening based on human historical patterns of conflict, when the actual intent is benign or neutral. Building AI systems that can handle truly alien contexts requires acknowledging the limits of training data and human experience. The flip side is that AI might be less biased than humans in certain ways. It doesn't carry emotional baggage about humanity's cosmic significance. It doesn't have nationalistic loyalties or religious commitments that color interpretation. An AI analyzing 3I Atlas trajectory data doesn't care whether finding alien technology validates or threatens anyone's worldview. It just processes numbers and reports probabilities. That dispassion could be valuable in situations where human judgment gets clouded by hope, fear, or ideology. Policy around space debris and planetary protection also intersects with interstellar objects. Current planetary protection protocols aim to prevent forward contamination carrying Earth life to other worlds, and backward contamination bringing extraterrestrial material to Earth that could harm our biosphere. These protocols were written for solar system exploration, assuming we're dealing with lifeless rocks or at most microbial ecosystems. An artificial probe changes everything. If 3I Atlas is a spacecraft, it might contain microbes from its home system, either as contamination or deliberately as part of its payload. Bringing such material to Earth laboratories requires containment protocols that don't yet exist at the necessary level of stringency. Conversely, if we send a mission to intercept 3I Atlas, we risk contaminating it with Earth microbes, potentially compromising scientific analysis of its composition. Sterilization procedures for spacecraft are well established for solar system missions, but are they adequate when the target might itself be biological or contain biological components? These questions sit at the intersection of microbiology, engineering ethics, and policy, requiring input from multiple disciplines. The draft UN framework acknowledges these complexities without fully resolving them. It establishes principles, transparency, international cooperation, caution, scientific rigor, but leaves implementation details to be worked out case by case. That's probably realistic given the diversity of possible scenarios. You can't write detailed protocols for every contingency when you don't know what contingencies might arise. What you can do is establish norms of responsible behavior and create mechanisms for rapid consultation when events demand decisions. National security considerations complicate international cooperation. If 3I Atlas turns out to be advanced technology, every nation with space capabilities will want access to study it, hoping to reverse engineer propulsion systems, materials, or computational architectures. Military applications of such technology could shift global power balances dramatically. The temptation to classify findings, restrict access, or even attempt to monopolize the object would be enormous. Balancing legitimate security concerns with the principle that extraterrestrial contact is humanity's shared concern requires delicate diplomacy and strong international institutions. Private sector involvement adds another layer. Companies like SpaceX, Blue Origin, and various asteroid mining ventures have deep space capabilities that rival or exceed some national space agencies. If a private entity detects something anomalous, are they bound by the UN framework? Legally, probably not directly, though their home governments might impose obligations through national regulations. Practically, the reputational and financial incentives probably favor transparency. Being the company that discovered alien technology and shared it with the world is good publicity. Being the company that tried to hide or monopolize such a discovery invites backlash lawsuits and regulatory crackdowns. Looking at 3i Atlas specifically through this governance lens, if perihelion observations show clear evidence of artificial propulsion, we'd likely see rapid convening of international consultations. Scientists would present data at emergency sessions. Governments would issue statements. The UN Security Council might meet, though it's unclear what action they could take. Space agencies would coordinate observation plans and potentially mission proposals. Media coverage would be intense and sustained. Public reaction would span excitement, fear, skepticism, and calls for various responses ranging from ignore it to shoot it down to send a welcoming delegation. The process would be messy, contentious, and slow compared to the event itself. 3i Atlas wouldn't wait for humans to reach consensus. It would continue on its trajectory, eventually leaving the solar system regardless of what we decide to do. That time pressure, the ticking clock of departure, would force decisions that might otherwise be deferred indefinitely. Sometimes constraints are useful. They prevent analysis paralysis and compel action even amid uncertainty. Connecting back to the opening stakes, if 3i Atlas reveals its true nature through an observable propulsion signature, we're not just rewriting astronomy textbooks. We're stress testing every institution, framework, and assumption we have about humanity's place in the cosmos and our readiness to engage with non-human intelligence. The draft UN protocols represent a start and acknowledgement that we need governance structures for scenarios that previously lived only in science fiction. Whether those structures prove adequate when faced with actual events remains to be seen. The ethical question at the core of all this: how do we respond to the unknown in ways that reflect our best values rather than our worst impulses? Fear can drive xenophobia, militarization, or denial. Greed can drive exploitation and secrecy, but curiosity, humility, and cooperation can drive discovery, understanding, and maybe even connection. 3i Atlas, whether artificial or natural, offers us a mirror. How we respond reveals who we are as a species, what we prioritize, and what futures we're building toward. That might be the most important test of all. Not whether the object is intelligent, but whether we can meet the moment with intelligence ourselves.